Good morning, children. Let's start our lesson number 4, carbon and its compounds. You all know very basic things about carbon. Means carbon is an element. The symbol of carbon is capital C. It is a non-metal. The name of carbon is derived from the Latin word carbo, which means coal. This is because carbon is the main constituent of coal. The amount of carbon present in the Earth's crust and atmosphere is very small. For example, the Earth's crust contains only 0.02% carbon in the form of minerals, and the atmosphere has only 0.03% of carbon dioxide gas. In spite of this small amount of carbon available in nature, carbon element has an immense importance in every sphere of life. The importance of carbon can be gauged from the fact that we are ourselves made of carbon compounds called organic compounds. In fact, all the living things, plants and animals, are made up of carbon based compounds, which are called organic compounds. Thus, carbon element is present in all living things. A large number of things which we use in our daily life are made up of carbon compounds. Our food materials like grains, pulses, sugar, tea, coffee, fruits and vegetables, etc. are carbon compounds. The materials like cotton, silk, wool, nylon, and polyester, which are used for making clothes, are carbon compounds. The fuels like wood, coal, kerosene, LPG, natural gas, CNG, petrol, and diesel, which we use for cooking food and running vehicles, are carbon compounds. And paper, rubber, plastics, leather, drugs, and dyes are also made of carbon compounds. It is clear that carbon element plays a very important role in our daily life. We can taste the presence of carbon in a material on the basis of the fact that carbon and its compounds burn in air to give carbon dioxide gas, which turns lime water milky. This test can be performed as follows: means burn the given material in air, pass the gas formed through lime water. If the lime water turns milky, then the given material contains carbon. Let's see why carbon always forms covalent bonds. The atomic number of carbon is 6, which means that a neutral atom of carbon contains 6 electrons. So the electronic configuration of carbon is 2, 4. It is clear that carbon has 4 electrons in the outermost shell, that is L shell of its atom. Since a carbon atom has 4 electrons in its outermost shell, so it should either lose 4 electrons or gain 4 electrons to achieve the inner gas configuration and become stable. Now, carbon atom is very small, due to which its outermost electrons are strongly held by the nucleus. So, it is not possible to remove 4 electrons from a carbon atom to give it the inert gas electron arrangement. It is also not possible to add as many as 4 electrons to a carbon atom due to energy considerations and acquire the inert gas configuration. It is obvious that the carbon atoms have to acquire the inert gas structure of 8 electrons in their outermost shell by the sharing of electrons. Since carbon atoms can achieve the inert gas electron arrangement only by the sharing of electrons, therefore, carbon always forms covalent bonds. Carbon is tetravalent. Second point. A carbon atom has 4 electrons in its outermost shell. So, it requires 4 more electrons to achieve the stable 8 electron inert gas electron arrangement, which it gets by sharing. Since one carbon atom requires 4 electrons to achieve the 8 electron inner gas structure, therefore The valency of carbon is 4. That is, carbon is tetravalent. The four valencies of carbon are usually represented by putting four short lines on the symbol of carbon. Third point, catenation means self combination. The most outstanding or unique property of carbon is its ability to combine with itself, atom to atom, to form long chains. For example, octane C8H18, one of the constituents of petrol, has a chain of 8 carbon atoms, and some of the organic compounds like starch and cellulose contain chains of hundreds of carbon atoms. The property of self combination of carbon atoms to form long chains is useful to us because it gives rise to an extremely large number of carbon compounds. This is because a long chain of carbon atoms acts as a backbone to which other atoms can attach in a number of ways to form a very large number of carbon compounds. The covalent bonds between the various carbon atoms are very strong and do not break easily. The reason for the formation of strong bonds by the carbon atoms is their small size. Due to the small size of carbon atoms, their nuclei hold the shared pairs of electrons between atoms strongly, leading to the formation of strong covalent bonds. The carbon atoms also form strong covalent bonds with the atoms of other elements such as hydrogen, oxygen, nitrogen, sulfur, chlorine, and many other elements. The formation of strong bonds by carbon atoms among themselves and with other elements makes the carbon compounds exceptionally stable. No other element exhibits the property of self combination, known as catenation, to the extent seen in carbon compounds. Silicon element shows some catenation property due to which it forms compounds with hydrogen having chains of up to 7 or 8 silicon atoms. But due to weak bonds, these compounds are unstable. Let's see occurrence of carbon. Carbon occurs in nature in free state as element as well as in the combined state, means in the form of compounds with other elements. In free state, carbon occurs in nature mainly in two forms, diamond and graphite. Another naturally occurring form of carbon called buckminster fullerene has been discovered recently. Please note that only a small amount of carbon occurs as free element in the Earth's crust. Most of carbon occurs in the combined state. In the combined state, carbon occurs in nature in the form of compounds such as carbon dioxide gas in air, carbonates like limestone, marble, and chalk, fossil fuels like coal, petroleum, and natural gas, organic compounds like carbohydrates, fats, and proteins, and wood, cotton, and wool, etc. etc. Let's see allotropes of carbon. There are three allotropes of carbon: diamond, graphite, and Buckminster fullerene. Diamond. Diamond is a colorless, transparent substance having extraordinary brilliance, or you can say shine. Diamond is quite heavy, is extremely hard. It is the hardest natural substance known. Diamond does not conduct electricity. It burns on strong heating to form carbon dioxide. If we burn diamond in oxygen, then only carbon dioxide gas is formed and nothing is left behind. This shows that diamond is made up of carbon only. The carbon dioxide formed by burning diamond can turn lime water milky. Since diamond is made up of carbon atoms only, its symbol is taken to be carbon. You can see the structure of diamond. The black balls represent carbon atoms. This tetrahedral structure, strong bonds exist between all the carbon atoms. Okay, so arrangement of carbon atoms in diamond is tetrahedral. Each carbon atom in diamond is joined to four other carbon atoms. A diamond crystal is a giant molecule, very big molecule of carbon atoms. Each carbon atom in the diamond crystal is linked to form to four other carbon atoms by strong covalent bonds. The four surrounding carbon atoms are at the four vertices of a regular tetrahedron. The diamond crystal is therefore made up of carbon atoms which are powerfully bonded to one another by a network of covalent bonds. Due to this, diamond structure is very rigid. The rigid structure of diamond makes it a very hard substance. It is the great hardness of diamond which makes it useful for making rock borers, for drilling oil wells, etc., and for making glass cutters. Please note that a diamond crystal has a tetrahedral arrangement of carbon atoms. The compact and rigid three-dimensional arrangement of carbon atoms in diamond gives it a high density. The melting point of diamond is also very high, being more than 3500 degrees Celsius. This is because a lot of heat energy is required to break the network of strong covalent bonds in the diamond crystal. Diamond is a non-conductor of electricity. This can be explained. See, we know that a carbon atom has four valence electrons in it. Now, in a diamond crystal, each carbon atom is linked to four other carbon atoms by covalent bonds, and hence all the four valence electrons of each carbon atom are used up in the forming the bonds. Since there are no free electrons in a diamond crystal, it does not conduct electricity. Our next allotrope is graphite. Graphite is a grayish black opaque substance. It is lighter than diamond. It is soft and slippery to touch. It conducts electricity. Graphite burns on strong heating to form carbon dioxide. If we burn graphite in oxygen, then only carbon dioxide gas is formed and nothing is left behind. This shows that graphite is made up of carbon only. The carbon dioxide formed by burning graphite can turn lime water milky. Since graphite is made up of carbon atoms only, its symbol is taken to be capital C. Let's see structure of graphite. The structure of graphite is very different from that of diamond. A graphite crystal consists of layers of carbon atoms or sheets of carbon atoms as shown in this figure. Each carbon atom in a graphite layer is joined to three other carbon atoms by strong covalent bonds to form flat hexagonal rings. The various layers of carbon atoms in graphite are quite far apart so that no covalent bonds can exist between them. The various layers of carbon atoms in a graphite are held together by weak van der Waals forces. Since the various layers of carbon atoms in a graphite are joined by weak forces, they can slide over one another. Due to the sheet-like structure, graphite is a comparatively soft substance. It is the softness of graphite which makes it useful as a dry lubricant for machine parts. Graphite is a good conductor of electricity. This can be explained. See, we know that a carbon atom has four valence electrons in it. Now, in a graphite crystal, Each carbon atom is joined to only three other carbon atoms by covalent bonds. Thus, only the three valence electrons of each carbon atom in graphite are used in bond formation. The fourth valence electron of each carbon atom is free to move. Due to the presence of free electrons in a graphite crystal, it conducts electricity. Just like diamond, graphite has also a very high melting points. Third allotrope of carbon which is recently discovered is Buckminster fullerene. Buckminster fullerene is an allotrope of carbon containing clusters of 60 carbon atoms joined together to form spherical molecules. Since there are 60 carbon atoms in a molecule of Buckminster fullerene, so its formula is C60. Buckminster fullerene is a football shaped spherical molecule in which 60 carbon atoms are arranged in interlocking hexagonal and pentagonal rings of carbon atoms. There are 20 hexagons and 12 pentagons of carbon atoms in one molecule of Buckminster fullerene. This allotrope was named Buckminster fullerene after the American architect Fuller because its structure resembled the framework of dome shaped halls designed by Fuller for large international exhibitions. The arrangement of carbon atoms in Buckminster fullerene resembles a football made of 20 hexagonal and 12 pentagonal panels, each corner of every panel representing a carbon atom. Buckminster fullerene is a dark solid at room temperature. It differs from the other two allotropes of carbon, diamond and graphite, in the fact that diamond and graphite are giant molecules which consist of an unending network of carbon atoms. But Buckminster fullerene is a very small molecule made up of only 60 carbon atoms. Just like diamond and graphite, Buckminster fullerene also burns on heating to form carbon dioxide. If we burn Buckminster fullerene in oxygen, then only carbon dioxide is formed and nothing is left behind. This shows that Buckminster fullerene is made up of carbon only. An important physical property in which three allotropes of carbon differ is their hardness. Diamond is extremely hard, whereas graphite is soft. On the other hand, Buckminster fullerene is neither very hard nor soft. Other properties of Buckminster fullerene are still being investigated. Okay, children, this much is enough. So please complete your notes. Next time we are going to see organic compounds. Thank you so much.